Hello, good morning dear students. Welcome to Interactive Virtual Class Nagaland once again. So students, we will continue with the chapter Magnetic Effects of Electric Current. So in our previous class, we have discussed about magnetic field lines. Yes, we have discussed about the region of magnetic field. We have also discussed how when we place a compass in a magnetic field, the compass needle gets deflected. Yes, students, can you recall? Then we have discussed about the direction of magnetic field lines in bar magnet. We have also discussed about direction of magnetic field lines using right hand thumb rule. Now, we have also discussed how a straight current carrying conductor behaves like a magnet. Yes, students, we have discussed how a current carrying conductor behaves like a magnet. So in today's class, we will see different types of magnet and different types of conductors. So here we have bar magnet, which we have already discussed in our previous class. Magnet has north pole and south pole. Yes, students. So let us quickly see again, the magnetic field lines in bar magnet. So here these are the magnetic field lines in a bar magnet. Now we have also discussed that the direction of magnetic field lines is from north to south. So the direction of magnetic field lines is in this direction. Okay. Now let us see using this magnet. Okay. So here we see a U-shape magnet. This magnet is known as horseshoe magnet. So we observe carefully. Okay. Here we see that even this magnet has north pole and south pole, and the direction of magnetic field lines in this type of magnet also, the direction of magnetic field lines is the same, that is from north pole to south pole. So this is what the magnetic field lines look like in U-shape magnet, also known as horseshoe magnet. Alright students, so the magnet can be in different shape, but the direction of magnetic field lines will always be from north pole to south pole. Now, in our previous class, we have discussed about straight current carrying conductor. So we have used straight conductor. Now, what if we use circular loop? This is not a straight conductor, this is a circular loop. So in today's class, we will see magnetic field lines due to a circular loop. So here we have circular loop, we have this setup, we have point A and point B. Okay, this circular loop will be connected to current. Okay, the positive end is connected at point A, negative end is connected at point B. Now let's see. Okay, let us observe the magnetic field lines due to a circular loop. So we have this setup, we have point A and point B. Take some iron fillings, and sprinkle on this board, on this board. So sprinkle the iron fillings. As you can see here, observe carefully. Alright. Now after sprinkling this iron fillings, turn on the switch and tap on this board for two or three times. Now when we turn on the switch, now we know that current is flowing through this conductor. Yes, students. So what is the direction of current at point A? If you remember, positive end is connected to point A, negative end is connected to point B. Now we have learned in our previous class that the direction of current is always from positive end to negative end. Yes, so here at point A, the direction of current will be upwards, because this is positive end, so the current will start from here and it will flow like this. So the direction of current at point A is upwards. Yes. Now if the direction of current is upwards, what will be the direction of the magnetic field lines? What is the direction of magnetic field lines at point A? Now we can determine the direction of magnetic field lines at point A by using right hand thumb rule. So if we hold this conductor in such a way that our thumb okay, is in the direction of current, then the finger that is curled around this conductor will show the direction of magnetic field lines. So here direction is upward, so the direction of current is upward, so direction of magnetic field line is anti-clockwise. It will be in this direction. So when direction of current is upward, the direction of magnetic field line is anti-clockwise. Now what is the direction of current at point B? The current flows from point A, starts from point A and it goes to point B. So when we see here, okay, we observe that the direction of current at point B is downwards. Yes, because the current is flowing from this direction. So here direction of current at point B is downwards. Now what will be the direction of magnetic field lines at point B? Yes, students, again we can determine the direction of magnetic field lines at point B by using right hand thumb rule. So hold the conductor in such a way that your thumb point towards the direction of current. Then the direction of your fingers curl around the conductor will give the direction of magnetic field lines. So here we see that at point A, direction of current is upward, so the direction of the magnetic field line is anti-clockwise. At point B, the direction of current is downward, the direction of magnetic field line is clockwise. Alright, so using right hand thumb rule, we can determine the direction of magnetic field lines. Now when we observe from the top, we see these are the magnetic field lines. Okay, these are the magnetic field lines. So here we see that at point A, okay, at this point, the direction of magnetic field line is anti-clockwise, and at point B, the direction of magnetic field lines is clockwise. It is because the direction of current is upward at this point, and the direction of current is downward at this point. Now, every section of the wire contributes to the magnetic field lines in the same direction within the loop. Now we have, see, this is a circular loop. So all this part are conductor, and the current is flowing all through this part. But in this activity, we have considered only at 2 points, that is point A and point B. Okay, we have considered only 2 points, that is point A and point B. But remember, every section of the wire contributes to the magnetic field lines in the same direction within the loop. So every section at this point, okay, or it may be at this point, every section of the wire contributes to the magnetic field lines in the same direction within the loop. Alright, students, now let us reverse the connection. Positive end, okay, will be connected at point B, and negative end will be connected at point A, and let us see, okay, the difference. So we have the same setup, we just reverse the connection of the current. So similar steps, sprinkle iron fillings, okay, sprinkle iron fillings on the board, then turn on the switch, okay, turn on the switch, then tap on the board for 1 or 2 times, and let us observe. So again we see some concentric circles form around point A and point B. So in this case, okay, positive end is connected at point B and negative end is connected at point A. So the direction of current will be from here, from point A to point B. So in this case, the direction of current at point B is upward. So the direction of magnetic field lines will be anti-clockwise. At point A, the direction of current is downward. So the direction of magnetic field line is clockwise. So here we see that when we reverse, okay, the direction of current, then the direction of magnetic field lines also reverses. So if we observe from the top, here we see, okay, at point B, the direction of current is upward. So the direction of magnetic field line is anti-clockwise. At point A, the direction of current is downward. So the direction of magnetic field line is clockwise. So we have seen 2 examples, right? When we reverse the connection of the current, the magnetic field lines direction also reverses. So magnetic field lines appear as straight lines at the center of the loop. Okay, so at the center of this loop, the magnetic field lines will appear as straight lines. Okay, at the center of the loop, the magnetic field lines will appear as straight lines. That is why we are able to see here, observe these straight lines here. Okay. Alright students, we have the first question for today. Please get your rough devices ready. The question is, two magnetic field lines. Okay. We have four options. I'm giving you 30 seconds to respond to this question. Your time starts now. So the question is, two magnetic field lines, option A, intersect at the neutral point. Option B, never intersect with each other. Option C, intersect near North Pole or South Pole. Option D, intersect at the midpoint of the magnet. So which of these option is the correct answer? Yes, students. Alright students, your time is up. Now if you have observed carefully, okay, we have discussed, okay, we have seen magnetic field lines of different magnet and different conductor. We have seen that the magnetic field lines, they do not intersect each other. Okay, so the correct answer for this question is option B, that is two magnetic field lines never intersect with each other. So option B is the correct answer. Very good students. Now, here we have two magnets. We have the thicker magnet in this case, and we have the thinner magnet in the second case. Now, if we observe carefully, this bigger magnet has more magnetic field lines, and this smaller magnet has less magnetic field lines. In our previous class, we have seen that the strength of magnetic field, it depends on the thickness of the magnet. Yes, students, can you recall? So here we see that strength of bar magnet, okay, strength of bar magnet increases with increase in thickness. So here this bar magnet is more thick. Yes, so there is more strength, so more magnetic field lines. In the second case, this bar magnet is thinner, so it has less strength, so less magnetic field lines. So remember this, strength of bar magnet increases with increase in thickness. Okay, the more the strength of the magnet, the more will be the magnetic field lines. So here this magnet is bigger, so it has more strength, so it has more magnetic field lines. This magnet is smaller, it has less strength, so it will have less magnetic field lines. So this is in case of bar magnet. Now we have discussed about circular loop. Yes, we have discussed about magnetic field lines in circular loop. What will happen, okay, or what happens if we increase the number of turns in a loop? In our previous example, we have discussed only about single turn, just one turn. But what happens, okay, if we increase the number of turns in a loop? So let us find out, okay. So here we have the same setup, but this circular loop has multiple turns, not just single turns. So sprinkle iron fillings, okay, on this board, and let us see. Now we have the same setup, so it is connected to current. Turn on the current, let the current pass through this loop, okay. Then what do we see here? We see more magnetic field lines than the number of magnetic field lines in a single turn circular loop. Do you agree? When we increase the number of turns in a circular loop, we see that there are more magnetic field lines. So what does this mean? Yes, students, it means that if there is a circular coil, okay, if the number of turns increases in circular loop, the strength of magnetic fields also increases. Okay, so if there is a circular coil having n turns, the field produced is n times as large as that produced by a single turn. So suppose we increase the number of turns of this circular loop by 10. Okay, we have, suppose we have 1 turn and 10 turns of the circular loop. Then the magnetic field, okay, the magnetic field produced by this circular loop having 10 turns will be 10 times more stronger than the magnetic field produced by circular loop with a single turn. Okay, so if circular loops have n turns, then the field produced will be as large as n times as large as produced by a single turn. So just like bar magnet, with the increase in thickness, the strength of magnetic field also increases. In circular loop, with the increase in number of turns, the strength of magnetic fields produced also increases. Alright? Alright students, we have another question. Please get your rough devices ready. The question is, if the number of turns in a circular coil is doubled while keeping the current constant, how will the magnetic field at the center change? Okay, we have 4 options. I'm giving you 20 seconds to respond to this question. Your time starts now. If the number of turns in a circular coil is doubled while keeping the current constant, how will the magnetic field at the center change? It will become half, it will remain the same, it will become twice as strong, it will become 4 times stronger. So which of this option is the correct answer? Alright students, your time is up. Yes, we have discussed that if the number of turns increase by n, then the field produced will also be n times as strong as it is. So here, number of turns is doubled. If it is doubled, then the strength of the magnetic field produced will also become twice as strong. So the correct answer for this question is option C, that is, it will become twice as strong. Alright? Alright students, now let us see another type. Okay? So here we have this structure. So in this case we see that this is also a circular loop. Yes, it is also a circular loop, but it consists of number of circular loop which takes the shape of a cylinder. Yes, so do you know what this is called? This is called as solenoid. Okay, so what is solenoid? A coil of many circular turns of insulated copper wire wrapped closely in the shape of a cylinder is called a solenoid. Okay, so solenoid is a conductor in the shape of cylinder. It consists of numbers of circular turns, and it is in the shape of a cylinder. Now let us see magnetic field lines due to a solenoid. Magnetic field lines due to a solenoid. So we have the same setup. Yes students, here positive N is connected at this end, negative N is connected at this end. We have the same setup. So let us see the magnetic field lines due to a solenoid. So when we turn on the switch, this is what we observe. Here we see the magnetic field lines due to a solenoid. Now remember, positive N is connected at this end, negative N is connected at this end. So here, how will we determine the direction of current and direction of magnetic field lines due to a solenoid? Yes students, how will we determine the direction of current and the direction of magnetic field lines? So observe carefully again. This is what the magnetic field lines look like due to a solenoid. Okay. Then bringing back this bar magnet. Let us see. Here we see the magnetic field lines due to a bar magnet. Yes students. So let us look at these two carefully. Do we see any similarities? Yes, right? They look similar. The magnetic field lines due to a solenoid and magnetic field lines due to a bar magnet, they look similar. So how do we know? We know that the direction of magnetic field lines in in bar magnet is from north pole to south pole. So here the direction of magnetic field lines is in this direction. But how do we determine the direction of magnetic field lines in terms of solenoid? Yes, students, let us find out. Okay, so here we have this setup. This solenoid is connected to this current. When we turn on the current, it will behave like a magnet, and so we will see this magnetic field lines. So what is the direction of current in this case? Yes, students, what will be the direction of current in this case? Positive N is here, negative N is here. But in this case, solenoid, it consists of many circular turns, right? So it goes like this. It consists of many circular turns. So the current flows from positive N to negative N. So current will start from here. It will turn like this in case of solenoid. So here we have this again we have our right hand. We will use right hand thumb rule to determine the direction of magnetic field lines. But here it is a little different from the bar magnet. In this case, this finger, okay, take your right hand and hold your hand like this. So this finger, the direction of the finger will give the direction of the current. Why? Because this is not a straight conductor. Solenoid is not a straight conductor. It has many circular turns. So current will go back, come front, go back, come front, go back, come front. So the direction of current is shown by the direction of the fingers in this case. Then the thumb, okay, our right thumb will give the direction of the north pole. Okay, will give the direction of the north pole. So here this is the positive end, this is negative end. So current will come from this, from the back to the front, from the back to the front, because it consists of many circular turns. So that means the direction, if this finger shows the direction of current, thumb shows the direction of north pole. So in this case, okay, we can determine the direction of magnetic field lines in solenoid with the help of right hand thumb rule. So what is right hand thumb rule in case of solenoid? So if you wrap your fingers in the direction of the current traveling in the solenoid, your thumb will point in the direction of the north pole. Now once we identify the north pole, we know that the direction of magnetic field lines is from north pole to south pole, right? So with the help of this right hand thumb rule, we can determine the direction of magnetic field lines due to solenoid or in the solenoid. So here we have this solenoid, okay, we have this solenoid, and this is what the magnetic field lines due to solenoid looks like. Okay, positive end is connected at this end, negative end is connected at this end. So let us observe carefully. This is what the magnetic field lines look like. Now here we see that in this case the direction of current is anti-clockwise. Yes, here we see that the direction of current is anti-clockwise. So the point, okay, where now solenoid has 2 points. It is in the form of a cylinder. It is in the form of cylinder. We have one end here. This is one end and this is another end. Solenoid has 2 ends. So the point or the ends where we observe that the direction of current is anti-clockwise, that is the north pole of the solenoid. Okay, so this is the north pole of the solenoid. Now if we observe at the other end, okay, if we observe at the other end of solenoid, we will see that the direction of current at this end or at this point is clockwise. Yes, so the direction of current at this point is clockwise. So the point where the direction of current is clockwise is the south pole in a solenoid. Okay, so here we have the south pole. So now we have north pole and south pole. We know that direction of magnetic field lines is from north pole to south pole. So here we can determine the direction of magnetic field lines in a solenoid. So the direction of magnetic field lines in solenoid is in this direction. Alright. Alright, students. So here we see when we turn on, when we turn on the current and allow current to pass through this solenoid, we have this magnetic field. So the current is in this direction. So this will be the north pole, this will be the south pole. And we also see the direction of magnetic field lines due to solenoid. Now what about the magnetic field inside this solenoid? Solenoid is in the form of a cylinder. So what about the inside of the solenoid? Let us see. The field is uniform inside the solenoid. The field is uniform inside the solenoid. We have discussed that the further we go away from this, the magnetic field strength decreases. Yes, but inside this solenoid, the magnetic field is uniform. Alright, students, we have another question. Please get your rough devices ready. The question is, if the direction of current in a solenoid is reverse, what happens to the direction of the magnetic field lines? We have 4 options. I'm giving you 30 seconds to respond to this question. Your time starts now. So we have seen the direction of current and direction of magnetic field lines in a solenoid. So what will happen if we reverse the direction of current? Option A is the direction of the magnetic field lines remains unchanged. Option B, the magnetic field lines inside the solenoid becomes weaker. Option C, the magnetic field lines outside the solenoid become stronger. Option D, the direction of the magnetic field lines reverses. Yes, students? Alright, students, your time is up, and yes, very good. The correct answer for this question is option D, that is, the direction of the magnetic field lines reverses. We have seen that the point where the direction of current is anti-clockwise is north, and the direction where the direction of current is clockwise is south pole. But if we reverse the connection of current, then this will become south pole and this will become north pole. So the direction of the, now if this become north pole and if this becomes south pole, the direction of magnetic field lines will be in this direction, because the direction of magnetic field line is from north pole to south pole. So the direction of the magnetic field lines reverses. Alright, students, we have another question. Please get your rough devices ready. The question is, the magnetic field inside a solenoid is which of the following? Option A is stronger at the ends than at the center. Option B, weaker at the ends than at the center. Option C, uniform along the length of the solenoid. Option D, non-existent at the center. So I'm giving you 20 seconds to respond to this question. Your time starts now. The magnetic field inside a solenoid is stronger at the end than at the center, weaker at the ends than at the center, uniform along the length of the solenoid, non-existent at the center. Alright, students, your time is up, and yes, excellent. The correct answer for this question is option C, that is uniform along the length of the solenoid. We have seen that the magnetic field inside the solenoid is uniform. So correct answer is option C. Alright, students, so here again we have solenoid. We have the solenoid. We have iron nail here. So we will do an activity. So take a soft iron. Take a soft iron. So we have this soft iron. Now bring it near the iron nail. Does it attract? No, right? The soft iron does not attract this iron nail because it is not magnetic. Now put this soft iron inside the solenoid. Turn on the current. So it allows the current to pass through the solenoid. Now bring this iron nail near this soft iron. Does it attract? Yes, right? So we see here magnetic effects. At first the soft iron did not attract this iron nail. But when we place this soft iron inside solenoid and allows current to pass through the solenoid, then we see that this soft iron, it behaves as a magnet and attracts the iron nail towards it. Yes, students. So here we see that when a soft iron is placed inside the current carrying solenoid, the soft iron acts as a magnet. Right? The soft iron acts as a magnet, and the magnet so formed is called an electromagnet. The magnet so formed is called an electromagnet. So let us see. Now, this solenoid is a current carrying conductor. Yes, so it produces magnetic field. This soft iron, when placed inside current carrying solenoid, it also behaves like a magnet. So what will happen to the magnetic field lines if we put them together? Yes, students, let us observe. Alright. So when we put a soft iron inside solenoid and turn on the switch, allowing current to pass through solenoid, this is what we will observe. Okay. So can you see any difference? Okay, any difference between the magnetic field lines of solenoid alone and magnetic field lines of solenoid along with this soft iron? Yes, students, we see that the magnetic field lines, number of magnetic field lines of solenoid alone is less, right? But when we place soft iron inside solenoid, we see that the number of magnetic field lines increases. So what does it mean? When there is more magnetic field lines, the strength of magnetic field is more, or it is stronger. Yes, students. So here, when a soft iron is inserted inside a current carrying solenoid, then the magnetic field inside the solenoid will increase. Okay, the magnetic field inside the solenoid will increase, and that is why we see that there is more magnetic field lines when a soft iron bar is placed inside the solenoid. Alright. Alright, students, we have another question. Please get your rough devices ready. The question is, when a soft iron core is inserted into a solenoid, the strength of the magnetic field increases, decreases, remains unchanged, becomes zero. So we have four options. I'm giving you 20 seconds to respond to this question. Your time starts now. When a soft iron core is inserted into a solenoid, the strength of magnetic field increases or decreases or remains unchanged or becomes zero. So A, B, C, D, which of this option is the correct answer? Alright, students, your time is up, and yes, good. The correct answer for this question is option A, that is increases. When a soft iron core is inserted into a solenoid, the strength of the magnetic field increases. Alright, students, we have another question. Please get your rough devices ready. The question is, which rule is used to determine the direction of a magnetic field around a current carrying conductor? Okay. Which rule is used to determine the direction of a magnetic field around a current carrying conductor? We have four options. The first is Fleming's left-hand rule. Option B, Maxwell's right-hand rule. Option C, right-hand thumb rule. Option D, none of the above. So we have four options. I'm giving you 30 seconds to respond to this question. Your time starts now. Which rule is used to determine the direction of magnetic field around a current carrying conductor? Fleming's left-hand rule, Maxwell's right-hand rule, right-hand thumb rule, none of the above. So which of these option is the correct answer? Yes, students. Alright, students, your time is up, and yes, very good. The correct answer for this question is option C, that is right-hand thumb rule. We use right-hand thumb rule, okay, to determine the direction of magnetic field lines around a current carrying conductor. You hold your right hand, okay, in such a way that your fingers curl around the conductor, and your thumb is pointing towards the direction of current, then the direction of your fingers, okay, will show the direction of magnetic field lines. Alright students, so in today's class, okay, we have discussed about magnetic field lines due to different shape magnet. We have seen in bar magnet, then we have seen in horseshoe magnet. We have also discussed about magnetic field lines produced by different shape conductor. In a previous class we have discussed about straight current carrying conductor. In today's class we have discussed about circular loop, yes, carrying conductor. The first we have discussed is magnetic field due to current through a circular loop of a single turn. First we discuss magnetic field. Magnetic field due to a circular loop, okay, of a single turn. Yes, students. Now we have also seen the direction of current and direction of magnetic fields. Magnetic field lines due to magnetic field in a circular loop of a single turn. We have also seen that if the direction of current is upward, the direction of magnetic field line is anti-clockwise. Yes, anti-clockwise. If the direction of current is downward, the direction of magnetic field line is clockwise. This is in case of circular loop. Now, when we increase the number of turns in circular loop, what happens? We have seen that bar magnet, as the thickness increases, the strength of magnetic field produced also increases. Yes, and if the strength of magnetic field increases, there will be more magnetic field lines. So we have seen that when we increase the number of turns in circular loop, we observe more magnetic field lines than in a circular loop with a single turn. So it shows that when we increase the number of turns in circular loop, the strength of the magnetic field produced also increases. We have seen that if we increase the number of turns by n, then the strength of magnetic field produced will also increase n times. Yes, students. Then we have discussed about magnetic field due to current in a solenoid. So what is solenoid? A solenoid is a coil of many turns of insulated copper wire wrapped closely in the shape of a cylinder. So we have seen magnetic field due to current in a solenoid. Yes, students. We have also discussed about right-hand thumb rule in case of solenoid. The use of right-hand thumb rule to determine the direction of magnetic field lines in solenoid is a little different, yes, than the use of right-hand thumb rule in bar magnet. In solenoid, the fingers shows the direction of current, thumb shows the direction of north pole. We have two ends in solenoid. Yes, students, we have two ends in solenoid. It is in cylindrical shape, so we have two ends. This is one end, this is the second end. So if one of the end, okay, if the direction of current at this point is anti-clockwise, okay, then this means that this point is the north pole of the solenoid. If the direction of current is clockwise, then this point, okay, is the south pole of the solenoid. If we reverse the connection of current, okay, and if this become clockwise, then the direction of the magnetic field lines will also reverses. Okay, so remember, students, direction of current is always from positive end to negative end, okay, and direction of magnetic field lines is always from north to south, okay, from north pole to south pole. But inside the conductor, inside the magnet, the direction of magnetic field line is from south to north pole. Okay, so this is inside the magnet or inside the conductor. But outside the conductor, the direction of magnetic field lines is always from north pole to south pole. We have also discussed about electromagnet, right? When an object behaves as a magnet when placed inside a solenoid, it is known as electromagnet. We have seen example of soft iron. Yes, soft iron core, it behaves as a magnet when placed inside a current carrying solenoid. So that is one example of electromagnet. We have also seen that when we place soft iron core inside solenoid, the strength of the magnetic field produced by solenoid also increases. Alright students, so this leads us to the last question for today. Please get your rough devices ready and give your feedback about today's class. I'm giving you 10 seconds for this question. Your time starts now. How do you feel about today's class? Yes, students. Alright students, your time is up. Thank you so much for your response and thank you for joining today's class. I will see you again in our next class. Till then, take care everyone and have a nice day.